Welcome everyone. My name is Gabriel Alvarado, a quantum algorithm engineer at Kipu Quantum. Today, I'm excited to introduce you to the Iskay Quantum Optimizer. This powerful tool leverages Kipu's cutting-edge bias field DCQO algorithm running on IBM's quantum computers to solve complex optimization problems. What's remarkable about this solver is that it requires only the objective function as input to automatically deliver problem solutions. It can handle optimization problems involving up to 156 qubits with a one-to-one mapping between classical variables and qubits. The optimizer enables the solving of higher-order unconstrained binary optimization problems, which include QVO and Ising spin glass Hamiltonians. To share a bit of insight into our tool, our algorithm employs an iterative, non-variational workflow combined with the digitization of counter-debating protocols, which results in quantum circuits with shorter depths and fewer entangling gates. In the bias field DCQO algorithm, after each iteration, the algorithm incrementally refines the evolved state, bringing it closer to the desired ground state. This is achieved by computing a so-called bias field from the solution measured in the previous iteration. Typically, around 10 iterations are sufficient for the algorithm to converge to a solution, which is significantly fewer than variational algorithms. How to use our Iskay Quantum Optimizer. First, I load the Iskay Optimizer from the Qiskit functions catalog, specify a problem and the IBM backend where the algorithm is going to be executed. Take the cost function shown here. We need 5 variables, 1 constant term, 3 single body terms, 2 two-body terms, and 1 higher order term of order 3. To specify this cost function, we write a dictionary in the following way. To run the optimizer, specify additional options, the number of shots, the number of iterations the bias field DCQO algorithm is going to perform, the use of a session, which is recommended given our iterative workflow of the algorithm. Run with an arguments dictionary, get a result in the form of a dictionary. Second example, I want to show that the way we index the variables in the cost function is quite flexible. And for example, where now the variables have integers that skip values. So they don't necessarily mean positions in a vector, but they work more closely as labels. To specify the cost function, provide a dictionary, formulate this cost function in binary, the options 5,000 shots, number of iterations equal to 5, same job tag. The result dictionary provided by the Iskay optimizer. Third example, to the max-cut problem, generate a simple 3 regular graph, 10 nodes, which translate to 10 qubits, create the terms that would correspond to the spin glass formulation of this cost function. Since the max-cut problem is essentially a QVO problem, all of the terms are of order 2 with constant terms. To specify the options, submit the job. Now the optimizer is providing directly the solution to the max-cut problem. Finally, just to show the last examples with bigger problems, I quickly import our benchmark instances, load using the PyGitHub dependency, max-cut problem with 32 nodes, specify both the options, the objective function, hit submit. The optimizer quickly finds the solution for us. In cases such as our benchmark instances with QVO problems generated from the heavy hex lattice, you can specify that the connectivity of your problem matches that of the hardware. Otherwise, keep it as false, which reduces the circuit depth. This marks the end of the demonstration. I hope it has been helpful. And please, if you have any feedback, contact us. We're happy to receive any comments. Thank you and goodbye.